taking a look at the properties of linear relations. So the table of values and graphs show the cost of a pizza with up to 5 extra toppings. So reading our table of values here, and looking at our graph, first off, I can see that this would be considered a linear relation. Linear because I could technically draw a straight line through these points. And I would expect that these points would continue on in the exact same fashion if I were to increase the number of extra toppings to 10, which is a very fully loaded pizza. So how does something become linear? Well, we have the exact same amount of graph, if you will, between each of our x values. So they go up by a consistent amount, meaning that we add 1 every time in this case. Okay, if we go up by multiples, it doesn't line up to be a linear function, and I'll show you why in just a second. Okay, so it's also linear because the increase between each point is the same amount each time as well. So we've added the same amount between each point in the y. So if we're looking at just a data table, I can tell it's linear because in this case, I'm adding 1 every time. Okay. Between my y values, the cost, I'm adding 0.75 every time. If I multiply, so I'm going to do a quick little table of values here. So if we have the x values and y values, if we have x equals 1, 2, 3, and 4, and y, let's say, is times 6 each time. Sorry. So we're going to times 6 each time. If we start with 4, times 6 is 24. Times 6, again, is 144. I have to get my calculator out here. And times 6 one more time is 864. So if I were to draw a graph of that, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, I am not getting a linear relation. I'm actually going to get something that is called an exponential, okay, or a quadratic. So it's going to curve upwards. It is not a straight line. So we have to be adding the same amount and adding the same amount here for it to be a linear relation. Even though we're multiplying by the same amount, it does not relate to a linear relation. So what patterns do you see in the table? Each extra topping is 75 cents extra is what I see here. Is plus 75 cents or, plus 0.75 of a dollar. And without any extra toppings, our base pizza costs $12. Okay, so write a rule for the pattern that relates to the cost of the pizza by the number of its toppings. So as you increase the number of toppings by 1, the pizza price increases by 0.75. All right, how are the patterns in the table shown in the graph? Well, we see that it is to the right and up by the same amount every time. So we can call this an increase, okay, because it's moving in that direction. How can you tell if the points from the table that the graph represents a linear relation? So how can we tell from just the table? So from just the table, I can tell that it represents a linear relation because we add the same amount to get to each y value every time. So for a linear relation, a constant change in the independent variable results in a constant change in the dependent variable. So we saw an increase, a constant +1 in our independent variable, and we saw a constant change in our dependent of 0.75. So this leads us to the idea of the rate of change. So the rate of change is the change in the dependent variable over or divided by the change in the independent variable. And now we usually think of the dependent variable as y, so we can write it as the change in y. Remember, a little triangle in math means change, okay, over the change in x. And change is always final point minus initial point. And we'll take a look at that in a little bit. But you need to remember your rate of change. All right, so which table of values represents a linear relation, and justify your answer? So let's look at the increase here. In our t values, do we have the same increase every time? Yes, we are adding 20. Again, we have to be adding or subtracting. We cannot be multiplying or dividing. In our n value, n increased by 1 here, so we add 1, and then we add 2, and then we add 4 plus 8 plus 16. So we're not adding the same amount, therefore this is not a linear relation. What's happening here is we're actually multiplying by 2 every time. So if I were to graph this, I would see a swooping up. All right, for the relationship between the amount of goods and services tax charged and the amount of purchase A, so A increases by 60 each time, and T increases by 3 each time. Oops. So this is a linear relation. All right, graph each equation below. And then we're going to determine which represent linear relations. So if you need to, you can make a table of values for these two. So I'm going to try and stay color-coded here. So x equals -2. X, so let's quickly label our graph here. 2, 4. Okay, so for our first one here, x equals -2. -2 is here. Oops, I've made a mistake in my notes. -2 is here, but there are no differences. All we have is x equals -2. I should have color-coded with red, sorry. Okay, for y equals 2.5, y equals 2.5 is right here. You should be drawing with ruler. Unfortunately, I'm not on my iPad here, so do your very best. So y equals 2.5, that's just going to be a straight line in this direction. Oopsie. So which one is a linear relation here? Y equals +2.5 is. X equals -2 is not a linear relation because it fails the vertical line test. Okay, for 2 and 4 here, I'm going to graph them on the other side. They're not as clear, so I may make a data table just to stay organized here. So this will be for 2, and I'll make one for 4 as well. So x and y values, x always is listed first. Okay, so let's have x equals -2, 0, 2, and 4. If I put in x equals -2 here, I get -2 plus 2.5, and that'll give me positive 0.5. If I put in 0 for x, I get 0 plus 2.5, that just gives me 2.5. If I put in 2 for x, I get 2 plus 2.5, which is 4.5. If I put in 4 for x here, I get 4 plus 2.5, which is 6.5. Graphing this data, -2 and positive 0.5, 0 and positive 2.5, 2 and 4.5, and 4 and 6.5. Connecting these, we should get something like that. Again, you should use a ruler if you have one available. All right, for number 4, let's put in, I'm going to put in a few extra values just to be able to show you what this looks like. So if I put in -2 here, I square -2, and that gives me positive 4. Positive 4 plus 2.5 is 6.5. If I put in -1, -1 times -1 is positive 1, plus 2.5 is 3.5. If I put in 0, I get 2.5. If I put in positive 1, 1 squared plus 2.5 is 3.5, and then 6.5 again. So -2, 6.5, -1, 3.5, 0 is 2.5, positive 1 is 3.5, 2 is 6.5. You can see here that we make a swoop. This is called a quadratic equation. It has a degree, an exponent of 2, and these both pass the vertical line test. Okay, so it has one discrete point for every domain and range value here. So both are functions in this case. So which relation is linear? Justify your answer. A dog sled moves at an average speed of 10 kilometers an hour along a frozen river. The distance traveled is related to time. So you could draw a graph or maybe make a data table. So we could say at time of 0, 1, 2, and 3 hours, we could look at the distance. So in 0 hours, they've gone 0 kilometers. In 1 hour, they've gone 10 kilometers. In 2 hours, they've gone 20 kilometers. In 3 hours, they've gone 30 kilometers. So we see that we're adding 10 to each side and we're adding 1 here. This is a linear relation, because we have a constant rate of change of 10 kilometers per 1 hour. Okay, so if we were to graph this, we would see a positive relation. The area of a square is related to the side length of the square. So we know that area is equal to length squared. So first off, our variable has a degree of 2. This is a quadratic, it's not linear, is what I know first off. However, let's prove it. So as L changes, let's see what happens to area. So length of 1, 2, 3, and 4. If I have a length of 1, I get an area of 1. If I have a length of 2, it's 4. A length of 3, 3 times 3 is 9. 4 times 4 is 16. So we have a constant rate of change in L, but we do not have a constant rate of change in A. If we looked here, we would get our exponential growth here, or a graph of L squared. It's not linear. A hot tub contains 1,600 liters of water. Graph A represents the hot tub being filled at a constant rate. Graph B represents the hot tub being emptied at a constant rate. Identify the independent and dependent variables. So our independent variable is the one along the x-axis. So the independent is time in minutes. The dependent variable is our y value, so it's our volume. Our volume depends on how much time it has been given to fill or empty. Determine the rate of change in each relation, then describe what it represents. So remember that our rate of change is equal to the change in our dependent over the change in our independent, which is the change in volume here over the change in time. So what we're going to do is we pick 2 points on our graph, and I'm going to write out the coordinates for that point. So we have 40, 800, and over here we have 0, 0. All right, so it's always the rate of change, in this case, is the change in our volume. So our final volume between the 2 points we picked, the final volume is 800. Take away our initial volume, which was 0, all over our final time, which was 40 minutes, Take away our initial time, which was 0 minutes. Now zeros here make it look like 800 liters over 40 minutes. If we divide those two, we get that it is increasing because it's a positive number, by 20 liters per minute. So this is how fast we are filling the hot tub. So for graph B, we're going to do very much the same thing. I'm going to pick 2 points and I'm going to write their coordinates. So this is a time of 0, a height of 1600, and this is a time of 20 minutes and a volume of 800. So again, rate of change is the change in volume. So the final volume in this case, which is 800 liters, take away my initial volume, which is 1600 liters, all over my final time, which is 20 minutes, take away my initial time of 0 minutes. This gives me negative 800 liters over 20 minutes. We're going to keep that negative because it tells me that my rate of change is decreasing, which makes sense because I'm emptying the hot tub. All right, so I get a negative 40 liters per minute. The negative means that it is dropping, so my volume is decreasing by 40 liters every minute. Doesn't matter which 2 points you choose on your graph, not at all. I could have taken these 2 points. I could have also taken these 2 points. I'm trying to choose nice data points that cross at perfect values so that it's easy to read. Here, I could have maybe taken this point too, doesn't matter, and this point. However, in science, what you want to remember is that you want to choose points furthest apart from one another on your graph. In science. In math, because we have very perfect data sets, it won't matter.